This is the first so-called MaxMin problem I'm going to be working with from the Foerster book. This is example 1 in section 8.3. What I'm told here is that I want to build a corral alongside a river. So basically it's going to have 3 sides. It'll be rectangular. Tells me that I have a limited amount of fencing. Okay, in this case I have 1,000 feet. And I want to figure out the dimensions needed to maximize the area of this corral. And of course, if we're talking about a maximum or minimum value, hopefully you can see a little bit of a potential calculus connection there. And now I'm going to go to the board and show you how this problem works.
All right, I'm going to talk a little bit about how to solve what are usually referred to as MaxMin problems, also called optimization problems. The recurring theme you're going to see in these problems is that you're trying to find either a maximum or a minimum value for some type of situation. Okay, another way of thinking of this is that you're trying to find the optimal value for some type of scenario. In most of these cases, you're going to have some type of constraints. You're going to have a certain amount of resources. Maybe you're trying to do something where you're trying to find the maximum volume, and you have a certain amount of metal or wood or something to create that item with. In this case, we're looking at something where we have a certain amount of fencing, and we're trying to figure out the maximum area that can be fenced in using this restricted amount of fencing. In profit problems, maybe you have only a certain amount of cost you can put into something, and it affects the profits in some way, and you want to maximize your profits based on those minimized costs. Or maybe you want to do something where you minimize costs of something by minimizing the amount of material used or that type of thing. So all kinds of different possibilities, really neat applications. It's one of the places where you really start to see the power of calculus. So we had this situation with the pen. Okay, there's a river. Unbelievably important when you're doing these problems to create a good picture, okay? The picture is just hugely, hugely, hugely important. So always create a diagram. And of course we saw the diagram in the book, but basically I'm trying to create this pen here. And the pen is 3-sided, okay? Now the way I'm going to set up this pen, we have a couple pieces of information here. I'm going to call this length in the x direction on the graph x, and I'm going to call the vertical values y, okay? Usually when you draw your picture, you're also going to want to set up your variables. And so those two things will kind of go together, okay? The other thing that typically goes along with the picture is you're very often going to have 2 different types of equations. You're going to have one equation that tells you something about your constraints, and then you're going to have an equation of something that you're either trying to maximize or minimize. Okay, so I'm going to write a constraints equation here. And the constraints equation in this case is pretty easy. Okay, my constrained value here is that I have 1,000 feet of fencing. Okay, really that's the perimeter that I have available for my fence. And I want to write an expression representing what's happening here. There's no reason for me to use less than my total amount of fencing, so I'm going to use it all. And I know that the perimeter of this shape, x plus 2y, has to add up to equal 1,000. Okay, so again, that's what's referred to as my constraints equation. It may not seem real clear what I'm supposed to do with this yet, but hold on, we'll get there. Okay, second part. You're going to be asked to maximize or minimize something in each of these problems. And so you need to identify that. And again, you're going to have a function that needs to be maximized or minimized. And hopefully you can see that there might be a calculus connection here. In this case, we're trying to maximize the area. So I need to write a function for the area. If you can write that function using one variable, that's great. Sometimes you're going to have to use the variables that you already set up in your earlier problem. For example, up here, I used 2 variables. So write it using the variables that you have. Your diagram and constraints may play some kind of a role in writing that final equation. So in a simplistic sense, area is equal to length times width. I'd like to write it using the variables from my diagram. So you'll notice here in this case that's going to be x times y. So I'm going to replace that. I have an x and a y. So we say that my equation is x times y. Now, here's the problem. If I was going to graph this, you'll see that technically I have an a variable and an x and y. 3 variables technically would have to be graphed on a 3-dimensional graph. It might give me some kind of curved plane or something. Not really anything that we know how to deal with. So what I really want to try to do here is write this in terms of one variable. Well, you ask yourself, how are you going to do that? How do I write this using either just x's or just y's? Well, remember that this is not the only piece of information I know going back to this problem. I also have the constraints. I have this second equation right here, and I can use that equation to write an expression to substitute in and figure out how I can find a way to replace one of these 2 variables. So for example, again, really depending on how you want to do this here, but I could write everything in terms of y in this equation. I could subtract 2y from both sides here, and I would know then that x was equal to 1,000 minus 2y. Okay? Anywhere where I see an x, I can substitute in a 1,000 minus 2y, and I'm going to get exactly the same thing. So this allows me to rewrite my area function. Area is going to be equal to 1,000 minus 2y times that other y value. And of course the area is going to be equal to, I'm going to write this as negative 2y squared minus 1,000y. Okay? That is the function that I'm trying to find the maximum or minimum value for. And it now includes my constraint values, which means I don't really have to think about those a whole lot more at this point. So then you say, well, how do I find my maximum or minimum value? Where do I go from here? Well, if you think about what that is, that's a parabola, okay? And in fact, if I want to graph this thing, let me do a little racing here, but I can make a quick sketch of what this thing is going to look like. First of all, we're really only worried about the first quadrant here. We need positive dimensions. So my function is, I'm going to rewrite this, I'll call this function a of y. Might have been better if we flip-flopped the x and the y, so this was written with an x variable if that bothers you, but it's going to be the same thing. Anyway, basically the function here is going to be negative 2y squared minus, oh, sorry, that's a plus 1,000y. And a couple different things I can do here. For example, if I want the x-intercepts, I can set it equal to 0, and I can factor out a negative 2y, and that's going to be y minus 500. And so basically tells me that this is going to cross the x-axis at either 0 or 500. So the graph looks something kind of like this, 500. Notice that it's an upside down parabola. Probably seems like the vertex is going to be something like this, okay? So the function basically is going to look like this. Now, this is a parabola, which means you can solve this using Algebra 2. You could use the vertex formula, x equals negative b over 2a, and you can find the vertex here. You could use symmetry, it seems like, because this graph should be symmetric, that's going to be halfway between 0 and 500. All kinds of different things you can do here. However, this is calculus class. What do I really want to do? I want to find that maximum value right there, okay? They're not always going to be parabolas. Sometimes they'll be 3rd or 4th degree equations or have an e or an exponential function or a log or something like that. The important thing here is the maximum value occurs when f prime of x, well, when f prime is, we don't have an x variable in this case, when f prime is equal to 0. Okay, so I'm going to find the derivative here. My function, a prime, is going to equal negative 4y plus 1,000. Okay, I want to know when that derivative is equal to 0. Okay, that'll be negative 1,000 equals negative 4y. Y is going to equal 250. Okay, and remember, this is my y-axis, this is my a of y. in this case. Okay, so at 250, my vertex value is going to take place. And again, you're going to want to go back and look at your final variables. What I found here is that this y value is 250. So I have a length of 250 there, and I can put that back in my original diagram, 250 over on that side. My x value, remember that constraints equation comes back into play. I know that y was 250, and of course the whole perimeter had to add up to 1,000. So I've used two 250s, and that'll leave me with 500 for my x value, okay? And of course, if you wanted to find the maximum area, you could multiply those two values out. And let's see, 5 times 25 is 125, and then we're going to have 3 zeros there. So it's going to be 125,000 square. I think the original problem was in feet. Yes, it is. Okay, so square feet. And by the way, very interesting, because your common sense might have suggested that you would want to maximize the area by making a square. And interestingly, because I don't end up using this side here, it turns out the maximum area is twice as long as it is high, and that actually maximizes the area. And again, if you don't believe me, try some different values, try to make it a square and see what that area would be, but it will not be as long. It will not be as large as that value there. So that's the basic concept. Draw a great diagram, use it to set up your variables, write a constraints equation based off any requirements about the variables, write the equation of whatever you're going to maximize or minimize, set that derivative equal to 0. That's where your maximum and minimum values are going to take place, and then you can put that back in your original equation. The concept is very simple, but you're going to have to find the relationships in each of these problems, and sometimes they can be easier than others. But hopefully that doesn't seem too bad.